Today's lecture will discuss the Kleene star as well as the positive closure. So, what is Kleene star? If we assume that sigma is the set of alphabet, then language in which any string of letter from this sigma is a word, even the null string epsilon. We call this language closure of the alphabet, and it is basically denoted by star after the name of the alphabet. That is, sigma star is basically known as the Kleene star. Kleene star. For example, if sigma is equal to A, alphabet A, then what is sigma star? Sigma star is equal to epsilon, then A, and so what is the meaning of this? It means the set of all string having 0 to infinity occurrences of A. So that is the set of all string having 0 to infinity occurrences of A is. Similarly, if we consider if sigma equal to A comma B, then sigma star is equal to epsilon A B A A B B A B B and so on. Meaning is the set of all strings made from either A's or B's or the combination of both A and B having 0 to infinity occurrences. And here we have written the word, that is, this is A, all are basically a word. So we write the word in increasing order of length, and we called this lexicographical order. These are basically lexicographical graphical order of basically they are arranged increasing order of length. That's why we call them the lexicographical order. Now we modify the concept, means uh, if sigma equal to A, we write a sigma plus is equal to A and so on. So this plus operation is sometimes is called the positive closure. This plus operation here, string of length is not considered. Now relation between Kleene star and positive closure. Positive closure. That is, the relation is basically A star is equal to A plus plus epsilon. Now we define the new concept which is basically known as a regular language. So now we'll discuss regular language. Regular language. Regular language. So what is regular language? Uh, a regular language is a formal language that satisfies some properties. So we define a regular language is a formal language that satisfies the following properties. Number one, it can be accepted by DFA, means deterministic finite automata. Number two, it can be accepted by non-deterministic finite automata. It can be described by a regular expression. Number four, it can be generated by a regular grammar. And it can be accepted by read-only Turing machine. It can be accepted by a read-only Turing machine. So a regular language that basically satisfies this property. Now, from this regular language, we'll discuss now the regular expression. So what is regular expression? Regular expression. Uh, in mathematics notation, what we have used? We have used some operator or some operations like plus, multiplication to build any expression, like suppose 3 plus 3 into 4. So it is an expression which is a mathematical expression, right? To build any expression like this by using these operations. Similarly, so what is the output of this? Here 24. So it basically gives you outcome 24. Similarly, we can use the regular operations to build an expression that describing this language, means regular language. And these expressions are basically known as the regular expressions. So what we can write, what is regular expression? So regular expression is basically uh, built upon or built up by using some regular operations, which basically describes the regular language. So we can write the regular expressions, regular expression operations, regular operations, we use regular operations to build what? To build up expressions describing language which are called regular expressions. Regular expressions. Regular expressions. For example, if we write, suppose 0 union on and then followed by 0 star. And the value of regular expression is basically a language. And in this case, the value is the language which basically consisting of all the string starting from 0 or 1 followed by any number of 0. In this expression, what is basically going on? So any string, set of all the strings which starts with either 0 or 1. This union means or. So 0 or 1 followed by any number of zeros. So thus, sometimes these notations are also used to make it is a concatenation symbol. Some books are basically use this notation like this. This is basically equivalent to 0 or 1, sometimes small, then 0 star. This notation are sometimes used for the concatenation. Right? It is for the concatenation we use. Now, how we explain these expressions? It means 0 or 1. Clear? Sometimes we use plus notation also. So, it basically consists of all the strings. The first symbol may 0 or 1. Clear? So, it means we can write in that way or 0 star. Or we can write in that way. 0 star means epsilon 0 0 0 0 0 0 and so on, because we expect this is a Kleene star. So if we, these are basically concatenation. So if we concatenate 0 with epsilon, it will be 0, then 0 with 0 0, it will be 00, then 0 with 00, so it will be 000 and so on. Similarly, 1 will be concatenated with epsilon, so it will be 1, then it will be 1 0, then it will be 1 0 0 and so on. In this way, set of what? So language will be generated. So this is basically the language. So what we have described, that set of all strings or language, or the value of this expression is the language which consisting of all string with a 0 or 1, like 0 or 1 and followed by any number of zeros. Look here. Yeah. So this is the basically the language of this regular expression. So it is basically a regular expression. Regular expression. Yeah, it is a regular expression. Now, how we define more explicitly these regular expressions? So, number one, phi epsilon and A belongs to sigma, all are regular expressions and they are basically called the primitive regular expressions. Primitive regular expressions, right? And number two, so phi means string, null or empty, and here string, epsilon is string of length 0 and a single symbol. Now, if R1 and R2 are regular expression, regular expression, regular expressions, then R1 union R2, R1, R2, concatenation of R2, that means R1 then followed by R2, R1 star and first bracket of R1 are also regular expressions. So R. Number three, any string is a regular expression if and only if it can be described from the primitive regular expressions by the finite number of application of the rule 2. So any string or a string is a regular expressions if and only if it can be described by or described from the primitive regular expressions by a finite number of applications of rule 2. This is rule 2. Now we'll give some more example like that. L of R language denote this basically denote the language associated with us. So language associated with R. R is any regular expression where R is any regular expression. So phi is a regular expression. It basically denoting the empty set. So L of phi is basically empty. Similarly, epsilon is a regular expression denoting L of epsilon is equal to this. For every A belongs to sigma and A is a regular expression, denoting by this. Okay. Now, as we have mentioned that If R1 and R2 are regular expressions, then language which are generated by R1 union or R2 can be written as L of R1 union L of R2, means language generated by R1 union language generated by R2. If language generated by R1 concatenated with R2 also is equivalent to language generated by R1, then language generated by R2 with concatenation. And L of R1 star, language generated by R1 star, which is equivalent to L of R star. Okay. So these are the some concepts. What is regular expressions? What is primitive regular expressions? And some of their properties. Now, if we write, for example, sigma of k, it means set of all string of length k. It means set of all string of length k. Now we'll give some example of the language corresponding to a regular expressions. Example 1. Suppose the regular expression is this. Okay. Now what will be the language generated by this? Obviously L of R equal to L of 0 or 1 star, which is basically equal to language L of 0, or we can write union L of 1 the star. So language generated by 0 or language generated by 1 the star. So it is nothing but 0 or 1 basically star, which is 0 or 1 of length 0 union 0 or 1 of length 1 union 0 or 1 of length 2 union, and so on. It means string of length by using 0 or 1, obviously it will be epsilon. Now union string of length consisting using 0 or 1, it will be either 0 or 1 union string of length 2 by the combination of 0 or 1, so it will be 0 0 0 1 1 0 1 1 and so on, right? Union this. So we can write epsilon 0 1 0 0 0 1 1 0 1 1 and so on. So this is basically generated. Example 2. Suppose we have a language, we have a regular expression of this. Example, suppose a regular expression R, which is basically 0 0. Then what will be the language generated by this? So L of R will be L of 0 0 star, which is basically L of 0 0. We can write this star also. And we can write language generated by 0 concatenation language generated by of 0 and it star. So it basically language generated by 0 is basically 0 and it is also 0. So nothing but this, and it means it will be epsilon, then 0 0, then 4 0 and so on. If we assume that 0 a equal to basically 0 0, then it will be epsilon, then a, and so on, right? And now put the value of a here. So that's why it will be the language will be this. So now here we have given some example of how regular expressions are basically corresponding to language, regular language. Now some other examples are also there. Look, if suppose uh, example 3, if sigma is equal to suppose 0 comma 1. Now what are the meaning of this? Number 1, 0 star 1 0 star. What is the meaning of this? Any number of 0, then 1, then any number of 0. That means the language that will be generated by this expression, regular expression, will be 1, then any number of 0, then that means 0 1, it will be 1 0, then it will be 0 1 0, then it will be 0 0 1, it will be 0 0 1 0 0 0, and so on. So the language generated by this can be written in that way. It will be any string w, and w contains at least one single one, contains a single one, right? Now if we write suppose sigma star 1, then sigma star, what is the language? What is the language? Look here. So it is basically, meaning is this, we can, in that way you can write 0 or 1 star, then 1, then 0 or 1 star. That means any number of occurrences or set of all string combining 0 and 1, then 1, again set of all string by combining 0 and 1. So we can write it will be like that: 0, then 1, then 0 0 0 1 1 0 1 1, and then followed by 1, right? This is concatenation, and then again same pattern: epsilon 0 1 0 0 0 1 1 0 1 1, right? Now if we concatenate all the things, it will be like that. uh, 1 will be, so in the left hand side and on the right hand side, if there is a string of length 0, then only epsilon will be there, but only 1 will be present here. So the string that will be generated contains at least 1 1. Clear? So we can write in that way: the language means string such that w contains at least 1 1. Clear? Now suppose example 3, if we write sigma star 0 0 1, then again sigma star, what is the meaning of this? It means we can write 0 or 1 star, then 0 0 1, we can write 0 or 1 star. So if it is epsilon, so it means any number of occurrences. On the right hand side, any number of occurrences, that means it can be epsilon, it can be epsilon also. So it must contain at least 0 0 1. Then that means 0 0 1 will be accepted. So the string here, it contains 0 0 1 as a substring will be accepted. So we can write the language that is string W such that W contains the string 001 as a substring. Yeah. So these are basically the some uh, example of the regular expression corresponding to regular language. So now we will discuss how or from regular expression how we can construct the NFA or non-deterministic finite automata with epsilon moves. Yeah. So from regular expressions to non-deterministic finite automata with epsilon moves. How we construct. Yeah. So there is some concept to construct this. We will discuss one by one. Number one, phi is a regular expression. Regular expression denoting the empty set. We know this. Denoting the empty set. Empty set. And the diagram will be, its diagram will be this. It is Q naught and it is QF, final state, without any arc. Without any arc. It is a state diagram for where no string will be accepted. There no string will be accepted. Now number two, epsilon obviously is a regular expression and primitive regular expression. Regular expressions denoting the set having only one string, that is epsilon, string of length 0, and the diagram or state diagram for this will be this. So we have mentioned in the previous class that if the initial state is a final state, then epsilon will be accepted. Clear? So if initial state is equal to final state, then epsilon will be accepted. Will be accepted. So it is its diagram, state diagram. Now, see, A is a regular expression denoting by this. So its state diagram will be, suppose Q naught, then QF, and arc will be labeled by A and this. So it is the state diagram for this A. Right? Now, some other concepts are there. If R is a regular expression, suppose P and Q are also a regular expressions or symbol or regular expressions. And say P and Q is symbol. So we can draw the state diagram. It will be look like this. State diagram is suppose this, and we can mark as epsilon, and then it will be P comma Q. But if R is suppose P or Q, then there will be two parallel lines. Suppose any state is Qi and it is a suppose state is Qi plus 1, then there will be it will be P and it will be Q. And if there is a concatenation like PQ, then its state diagram will be it will be suppose Qi, it will be suppose Qi plus 1, and it will be suppose Qi plus 2. Now it will be P and it will be Q and this. And if it is a R, suppose A star or P star, then we can, it will be loop. Suppose, and it will be Q star, then it will be P and this. Clear? So these are some state diagram corresponding to our regular expressions. Now, we will give example how we construct these regular expressions. Suppose we are given R1 is one regular expressions and R2 is another regular expressions. Suppose R1 is regular expression like this. Suppose it is a machine, suppose M1, right, which accept this regular expression R1. Clear? So we assume that this is a machine M1 which accepts R1, and its transition diagram is this. And R2 is another regular expression. We assume that it is M2. Clear? And it is also represented by R2. Now, how we construct this R1 plus R2? That means R1 union R2. How we construct this? So, the rule is basically we have to introduce a new initial state. We have introduced a new initial state. Done. And we have to remove no more initial states. We see that the machine M1 has one initial state and M2 has another initial state. M1 accepts R1 and M2 accepts R2. We have to remove these initial states. Now, we redraw these two machines, that is M1, here this, clear, and we draw this, here the machine is M2. And we have to draw arc from this newly introduced initial state to this initial state and this initial state with label arc as a epsilon moves. And again we have to introduce another new final state and remove no more final state. This final state will be removed. So it will be non-final state. It will be non-final states. And we have to draw an arc from this to the newly introduced final state with arc label epsilon, and from this with arc label epsilon. Now, if this machine, so it is basically a new machine which recognizes this R1 or R2. So now if R1 accepts the language L1, and if R2 accepts language L2, then the system will accept L1 union L2. That means we can write L1 union L2 is basically string such that X belongs to the language L1, or this is basically or X belongs to the language L2. Right? So in this way we can represent R1 plus R2. The R1 and R2 are both of the regular expressions, and R1 accepted by machine M1 and R2 accepted by machine M2. Two different machine accept. Now we can do this. So this is basically the representation of this R1 plus R2. Now how we explain this? And this is basically the NFA. It is basically the NFA with epsilon moves. So now if a string accepted by the machine M1, so obviously it will accept the language L1, and if any string is accepted by the machine M2, that means it accepts the language L2. So we have represented two different regular expressions, and the representation of the regular expression R1 plus R2. Now we'll give another one. Suppose we want to design machine that is that accept language L1 and L2. Clear? And we have two machines like M1 and M2, where M1 accepts R1 and where M2 accepts R2. Now we have to design this. Clear? L1, L2. L1, L2 means language. Suppose L1 accepts language X and L2 accepts language string X and L2 accept string Y. That means XY such that X belongs to the language L1 and Y belongs to the language L2. We have to design. How we can design this? We can design by using this. Initially the machine M1 will be there, and there is another machine M2 which accept this. So it basically accept X, right? It accept X and this machine will accept Y. That means from some initial state, if the machine accept this, that means it will accept X. And in machine M2, if this is initial state and this is the final state, then this machine will accept Y. And we have to make, when we have to concatenate these two strings, we have to concatenate by using this an arc drawn from the final state of M1 to initial state of machine M2, and M1 machine's final state will be removed. And we have to make an arc with level epsilon. And the machine M2, this will be the final state, and this will be the initial state. So now this machine will accept X, Y, where X belongs to language L1 and Y belongs to language L2. Now we design L1 star, that is language which is accepted by R1, and that is Kleene star, L1 star. Okay. So how we can design this? So the design will be look like this. As we know, the machine is M1. So the machine M1 which accepts R1, that means it is initial state and this is the final state. And this is the machine M1, it is an initial state. And it accepts the regular expression R1, right? Now the language L1 star means set of all strings from 0 to infinity occurrences, right? So how we can design this, that L1 star? Clear? We know that L1 star means language with a string of length 0 or string of length 1 or string of length 2 and so on. In this way we can, all the strings will be there, or language generated by this actually. Basically it is empty string. Now we can design by using this. So this is initial state and this is a final state suppose. And we have to introduce a new initial state. We introduce it and we have to make an arc from this newly introduced initial state to previously initial state, and no more initial state will be there. And we have to introduce another final state and we have to mark an arc, make an arc from this previously uh, uh, final state to newly introduced final state, and no other final state will be there. And what does it mean? It means from this initial state, by taking epsilon transition, we go to this state and we will accept language L1 by traversing this path. Clear? Suppose our language is, it looks like this. Suppose mm, 0. We'll give an example later one, but now suppose it is 0 star. Suppose equation 0. So now R1 is equal to 0 star. So it will be epsilon 0, 0, 0 and so on. So we first consider this, then we will consider the epsilon accepted, because the language accepted epsilon 0, 0, 0 and triple 0 and so on. Now from this state, by taking 0, by processing 0, clear, we can move to this state, and through epsilon moves we can accept it. Now when we have a 0, 0, that means by taking epsilon moves we move to this state, and reading 0 we move this state, and without reading any symbol, that means epsilon, we move this state, again read 0 and it will be repeated. And after, when the string exhausted, after reading epsilon, we reach to the final state. So this machine only accept L1, this just accept L1 only, but not star. That means epsilon will not be accepted. Now how we make epsilon accepted? So we have to make another arc labeling start or initial state to the final state with label epsilon. So this machine now accept epsilon. That means it is the complete design of L1 star. It means also we can write in that way. It will be, suppose x, I and j. That means string xij, where each of xij is belongs to L1, language L1, each of this. Now we'll give a complete example for this. Suppose suppose uh, suppose suppose we have a regular expression r equal to 0 or 0, 1 star. Now we have to design a NFA with epsilon moves corresponding to the regular expression. Now in this regular expression, obviously 0 will be accepted and 1 will be accepted. How we can represent this? Because 0, 1, these are the primitive regular expressions, and we can represent in that way. 0 will be accepted. So 0 will be accepted. You have to make an initial state, you have to make a final state, and there will be an arc with level 0. Similarly, 1 will be accepted. How? Initial state, you have to make a final state, and 1, this one will be accepted. Now, how 0, 1 will be accepted? 0, 1 means, as we have mentioned that L1, L2 in the previous slides, or in the previous examples, where this is basically L1, L2. So here 0 and 1, this is a 0 followed by 1, there is a concatenation, right? So it is a concatenation, so we can write 0, 1 will be accepted. How we can design this? We have to, we can consider that it is M1 machine, and we can consider that it is M2 machine, right? It is M1, M2, where M1 accepts 0 and M2 accepts 1. Now we have to design 0, 1. So it will be look like this. Initial state, then 0 will be accepted, 0 will be given here, and there will be an arc with level epsilon. Again, the initial state of machine M2, level 1, and it will be the final state. Look here. Now here 0, 1 will be accepted. Now we have to accept 0 or 0, 1, right? So we have to accept, so to accept 0 or 0, 1, how we can design this? So it is basically parallel, right? 0 or 0, 1, as we have mentioned in this example, R1 plus R2. Here R1 means 0 and R2 means 0, 1, right? So we can assume that it is R1 and it is R2. So we can design in this way. So 0, it accepts 0, we write in this way, and we have to introduce another machine. So it is M1, we can consider that it is M1, it is M2, right? Here in this case. So now this will accept 0 followed by epsilon, this will accept 1, then it will be in the previous case, it will be final states, because 0 will be accept final state and final state. Now just for simplicity we make this, right? So now this branch basically accepts 0, 1, and this branch basically accepts 0. Now we have to accept 0 or 0, 1. That means we have to introduce a new initial state and make transition from here with epsilon and make it the initial state. We have done this. We have to introduce another final state newly introduced, and we have to make an arc from here with epsilon moves. We have to make an arc from here with epsilon moves. Now we have to remove this. Clear? So now this machine, it is a machine which accepts 0 or 0. Now we have to accept 0 or 0, 1 star. How we can do this? Okay. So now we remove first this. Not necessary. We can use it. Now, as this machine accepts 0 or 0, 1, right? Now we have to accept 0 or 0, 1 star. Okay. So to accept 0 or 0, 1 star. So before considering epsilon, so any string, these are basically combining by using 0 or 0, 1 will be accepted. So if the string is suppose 0, then from this initial state by taking epsilon moves, reading 0 and taking again epsilon moves, we reach the final state. Now when 0 1 comes, so we have to go from this state to this state with epsilon moves. Because suppose 0, then 0 1, then suppose 0 0, then 0 1 0 1. These will be the uh, strings that we need to accept, and this is basically the language, right? So now it will accept this, but now in this star there is another epsilon, that is string of length 0, which need to be accepted. So to accept this, we have to introduce another new initial state. We introduce it and make a transition from this state to this with the epsilon moves. Done. And and we have to introduce another final state, right? Obviously previous case in this 0 0 1 0 0 0 1 0 1, in this scenario also we have to make this. Now we have to make this epsilon, and we have to make it no more final state, right? Now this will accept all the string except epsilon. Now we have to accept this epsilon. How we can do this? We can do this by incorporating an arc from initial state to final state with label epsilon. Now this will accept this 0 or 0 1 star. So in this way, we can construct a NFA with epsilon moves from the regular expression, from any regular expressions. Yeah. Now if we want to construct DFA from this NFA, obviously we know first we have to remove this epsilon from this NFA with epsilon moves. So from NFA with epsilon moves to, we have to construct NFA without epsilon moves. Then using the subset construction method, we can convert this NFA to a DFA. Now we'll give another example. Uh, we remove this. Okay. We will remove this and we'll give another example. Suppose uh, we have to represent a regular expression which is basically set of all strings over 0 1 ending with 0 0. So what will be the regular expression corresponding to this? So set of all string over 0 1 ending with 0 0, that means at the end there will be 0 0 every string, and the string will be the combination of 0 or 1 with a star, and its corresponding diagram directly we can write in that way. Its corresponding diagram will be as we know, 0 or 1 star means we can write in that way, it is 0, or we can write it is 1. Suppose it is q naught, and then followed by 0, and then followed by 0, then it will be the final state, accepted state. So this will be the diagram corresponding to this regular expression. So it is a regular expression, it is corresponding its diagram where the machine will accept this. So the smallest string that will be accepted by this diagram is 0 0. Obviously, if it gives epsilon string of length 0, then only 0 0 will be accepted. Right? Now, suppose we'll give a few more example. Suppose set of all string over 0 or 1 beginning with 0 ending with 1. So next, set of all string over 0 1 beginning beginning with 0 and ending with 1. What will be this? So its corresponding regular expression R will be beginning 0 ending 1 and between any string, set of all string. So it will be 0 or 1 star. So you can draw the diagram like this. So the smallest string which will be accepted is 0 1. So you have to design a diagram where it will accept 0 1. So it will be 1, it will be 0, and in between any number of 0 1 may be there. All are basically, here it is an NFA in nature, right? Q0, Q1 and Q2. NFA. Okay. So thank you. So in this lecture, what we have discussed, we have discussed what is Kleene star and positive closure. Then we have discussed the regular language, then regular expressions, and what are basically the regular expressions and how we can represent that a from regular expressions to a language, and finally we have converted from a regular expressions to, or we can represent regular expressions to a non-deterministic finite automata with epsilon loops. Thank you.